Chapter 2 is acids and bases, and again, this is one of our 5 areas that I talked about since the beginning. Were really vital concepts to understand organic chemistry. This is what's going to help keep organic chemistry from becoming something you need to memorize, but it gives you the concepts that you're going to use to solve things. So if you remember again, areas A is acid-base, R resonance, E electronegativity polarity, another A aromaticity, and S sterics. So in Chapter 1 we looked at resonance and electronegativity and polarity, and in Chapter 2 we're going to look at acids and bases. So we'll start with Bronsted-Lowry acids and bases. We'll skip to Arrhenius acids and bases that you might have learned in Gen Chem, because Arrhenius acids and bases really only work in aqueous solutions. That's by definition. So Bronsted-Lowry acids and bases. So to begin with, a Bronsted-Lowry acid is a proton donor. And one of the things that you'll notice is that in organic chemistry, when we talk about H pluses, we'll call them a proton. And I'll write it H plus, but I'll say proton. And the reason why, if you think about it, is if you have a hydrogen atom, you've got a hydrogen nucleus that has 1 proton, and you've got 1 electron out here somewhere flying around the nucleus. So if we take that electron away, and all we have is a hydrogen nucleus, there are no neutrons in there. If there's a neutron, it would be deuterium instead of hydrogen. If we only have the hydrogen nucleus, we take away its electron, what we're left with is a proton. So we'll write H plus, but as I'm reading that, I would say that an H plus donor is a proton donor. And then a Bronsted-Lowry base is a proton acceptor. So to be able to form a new bond to a proton, or to accept a proton from somewhere, it must have an available electron pair somehow. Right, there's 2 ways that you can get an available electron pair. One is a lone pair of electrons, and the other is to be from a pi bond. If you remember from last chapter, when we looked at the strength of pi bonds versus sigma bonds are significantly weaker than sigma bonds. They're much easier to break, and so we can use pi bonds to form a new bond with a proton. So what are some common Bronsted-Lowry acids? Things that you already know, like HCl, hydrochloric acid, sulfuric acid, H2SO4. Water is a Bronsted-Lowry acid. Alcohols are Bronsted-Lowry acids. Carboxylic acids, like acetic acid, are all good examples of Bronsted-Lowry acids. What are Bronsted-Lowry bases? So this is going to be a bigger category, because the category for Bronsted-Lowry acids are things that have an ionizable proton that will come off. A Bronsted-Lowry base can be anything that has a lone pair or a pi bond. So it can be anything from an amine to hydroxide. It's a common one that you remember from Gen Chem. Amide ion, NH2 minus. It could be H minus, a hydride. Could be an alkoxide, which is an alcohol that has been deprotonated. Could actually just be an alcohol. Or water. Remember, there are 2 lone pairs of electrons on the oxygen and water, so water can be a Bronsted-Lowry base. And it could be alkenes. It could be carbonyls, things with carbon-oxygen double bonds. And those are just some examples. One of the things that you'll notice, hopefully, is that you have certain molecules like water that can both act as Bronsted-Lowry acids and as Bronsted-Lowry bases. If you remember that from Gen Chem, we'd call that molecule amphoteric or amphoprotic. Work either way. So either amphoteric or amphoprotic. Those are molecules that can act as acids or bases.